We have already seen that individual atoms and molecules are incredibly small. So when we talk about macroscopic quantities of compounds, it's helpful to define a new unit for the number of atoms or molecules that could conveniently fit into the palm of your hand. That unit is called a mole. At the simplest level, a mole is just a particular number of atoms or molecules. Just as a pair is 2 of any similar objects, a dozen is 12 of them, and a gross is a dozen or 144. A mole of objects is 6.022 times 10 to the 23rd of them. It's a huge number because atoms and molecules are just so tiny. This number is called Avogadro's number. Technically, a mole is defined as the number of carbon atoms in exactly 12 grams of carbon-12. It turns out that because the atomic mass unit is also defined in terms of carbon-12, a mole is the number of atomic mass units in 1 gram of anything. A mole of carbon-12 atoms has a mass of exactly 12 grams, by definition. So we say that the molar mass of carbon-12 is 12.00 grams per mole. Natural carbon, which includes small amounts of carbon-13 and carbon-14 isotopes, has a molar mass that's slightly larger, 12.0107 grams per mole. Similarly, oxygen has a molar mass of 15.99 grams per mole. You can read these numbers right off the periodic table because the molar mass in grams per mole is exactly the same value as the atomic mass in atomic mass units. To calculate the molar mass of a molecule like CO, carbon monoxide, simply add the atomic mass of carbon and oxygen. For ethyl alcohol, which has an empirical formula C2H5OH, add up the atomic masses of 2 carbons, 1 oxygen, and 6 hydrogens. Likewise, uranium hexafluoride has a molar mass of 352.02 grams per mole. Now we can convert between grams, moles, and atoms. For example, we can find the mass of a 2.6 carat diamond by multiplying by 0.2 grams per carat to get 0.520 grams. If we divide this number by the molar mass of carbon, we get 0.0433 moles. Note that the grams units in the numerator and denominator cancel out, and the moles moves up to the numerator of the answer. Finally, we can calculate the number of atoms in this diamond by multiplying the number of moles by Avogadro's number. The final answer, 2.61 times 10 to the 22 atoms, is written here in a shorthand scientific notation that's used by most computers and calculators. Many materials do not exist as discrete molecules, but we can use the same techniques on the formula unit, which is the smallest uncharged repeating unit of atoms in the compound. Sodium chloride has a formula mass of 58.44 grams per mole. So a container of salt that you might purchase at the grocery store contains 12.6 moles of sodium chloride. Molar masses are also useful for determining the empirical formulas of molecules. Suppose that we start with a sample of unknown but pure compound, and a standard elemental analysis shows that it contains carbon, hydrogen, oxygen, and nitrogen in the percentages by mass shown in the first column. If we divide each value by the molar mass of the element, we convert the mass ratios to mole ratios. Then if we divide all the numbers by the smallest value, in this case 1.6385, we convert the mole ratios to whole integers. The empirical formula of the compound must therefore be CH3O2N, because the formula unit contains 1 carbon, 3 hydrogen atoms, 2 oxygen atoms, and 1 nitrogen atom. Unfortunately, this analysis does not tell us anything about the connectivity of the atoms in the molecules, and there are at least 3 possible structural isomers that all have this same empirical formula. Note that sometimes the methyl group, which is a carbon bound to 3 hydrogens, is often written as CH3, or in this case H3C since it's on the left-hand side of the molecule. Also, in the last structure on the right, it is understood that the atom lying at the vertex of the stick structure is a carbon atom, even if we don't write the letter C explicitly. The number of molecules is proportional to the number of moles, and the proportionality constant is Avogadro's number. So solution concentrations are normally expressed in units of moles per liter, or molar, which is denoted by a capital M. To make a 1 liter solution of sodium chloride at a concentration of 0.2 molar, we just have to add 0.2 moles of sodium chloride to enough water to make a 1 liter solution. But our scales weigh only mass, not moles. So first we must calculate the mass of 0.2 moles of sodium chloride, which is 11.7 grams, and then weigh out that much salt to add to the water before completely filling the volumetric flask. You should practice converting from grams to moles to molecules and back again, because you'll do this a lot in chemistry problems. The reason is that reactions take place between molecules, but balances only measure mass. Moles are a convenient measure of the numbers of molecules in a sample because for most substances, a mole of something is a quantity that can be used in a laboratory experiment. Think of it as an amount of substance that fits easily into the palm of your hand.